Welcome back, everyone. Today we're going to be talking about binomial trials. They're also called Bernoulli trials. And we're going to start with simple examples, and then we'll go to the more complicated examples. And at the end, I'm going to show you an example where it looks like you're going to need binomial trials, but you don't, right? You don't need them. So why is that important then? It's because probability and statistics is such a broad subject that you might know the different techniques, how to use them. Like you might know how to go in the Z tables, find the probability, or calculate the probability if you're given statistics like 72% or whatever, or calculate the probability of some dice experiment or some card experiment, or from permutations and combinations. And there's hypothesis testing, there's confidence intervals, there's all of these different formulas, for mutually exclusive events and so on. So it can get confusing in terms of when do you actually need to use these binomial trials. So it's important to know how to use them, yes, but also know when to use them, right? So we start with simple examples. So this is 4 examples that you have, and so question 1, you have a factory produce light bulbs, and 93% of them are defect free, which means they are okay. If a random sample of 10 bulbs is taken, what is the probability that exactly 3 are defective, right? So you have another problem here, question 2, a multiple choice test. Each question has 4 answers. A student guesses all questions. What is the probability that they get exactly 5 correct out of 10, right? You have another question. You have a basketball player. They have 72% free throw shooting range, so shooting percentage. So they have a statistic that 72% of their shooting goes in, and then you have 20 free throws. How many? What is the probability that exactly 16 goes in, right? And then you have another question. A company, they make smartphones. 91% of their smartphones are taken for quality test, and it was found that 10% of those are defective. And to ensure quality, a sample of 13 of those are selected randomly for additional check. So what is the probability that exactly 3 of the 13 selected are defective? Right, so these examples are somewhat similar. Simple examples. I'll explain why I'm saying simple examples. They're somewhat similar, and you usually take the same steps to do each of those examples, right? So this is the formula for binomial trials. It's a simple formula. It only has 3 variables, 3 things in this formula. So first of all, how do you recognize the question is a binomial trial, right? So they usually give you a statistic either in percentage form, like the basketball player, 72% free throws go in, or the maths test, they give you 1 in 4, right? 1 in 4 of those it's the correct answer. Or the smartphones, they told you 10% are defective, right? So they give you some statistic of failure or success, right? And how else do you know it's a binomial trial? There's only 2 possibilities: either you success or you fail, right? It's not like card games where you have a red card, a jack, a queen, and whatever. So you have all these different choices. So it's not a binomial trial. So in this case, it's usually machines, or a go or not a go, or something like that. There's success or failure. So there's 2 distinct things, right? And that's how you know it is a binomial trial. And also, so they give you the statistic, they give you there's a probability of success or failure, and they usually use these words like at least, or at most, or exactly. So exactly is the most used one. So they want an exact number to choose from. So they say they chose 10 samples. What is the probability that 3 of them are defective? Or what is the percentage that 3 of them are okay? So that's how you kind of know it's a binomial trial question, right? When you have these kind of things. So in this case, you have these 3 variables. The formula can look complicated to someone else, but it's actually not. Just remember it's 3 variables. Once you extract them from the question, then the last thing is just to sub them into the equation, and then you have your answer. Let's look at question 1. A factory produces light bulbs. 93% of them are defect free. That's a statistic, right? And then in a random sample, 10 bulbs is taken, and then what is the probability that exactly 3 are defective? So I know it's a binomial trial question. The next thing I do, write down the formula, right? That's the formula, and then I'm just trying to hunt the x, the n, the p. So what is the x? The x is the number of successes that I want, right? In this case, success is quotation marks because it means what I want, right? In this case, I want to find 3 defects. So defective, being defective in this case is the success, right? So in this case, x will be 3, the number that I want to be successful, or that I want, the number of things that I want. I want 3 of them to be defective. So x is 3, right? N is the number of trials. So I have a pool of 10 bulbs, and I want to get 3 of them to be defective. So 10 is the trial. So I take 10 bulbs one at a time and I test is it defective or not. So I have 10 trials, or 10 possibilities that I can pick, 10 samples in there that I can pick from, right? And then P is the probability of success, right? I get success in quotation marks because in this case, our success is actually finding defective bulbs, right? So in our case, probability of being defective, it's actually not 93%, right? 93% is the probability of being okay or defect free. So the chances of you being defective, because the binomial trial, it will be just 1 minus the probability of being defect free. So if I know 93% are good, that means 7% are bad, right? There's no in between. That's a binomial trial. There's no some other option like they are, maybe. There's nothing like that. It's either fail or success, defect or defect free, right? So our P in the question, in the formula, I'm just going to fill in the formula, right? The formula is n choose x times p to the power of x bracket 1 minus p to the power of n minus x, right? So I'm just going to set that into the formula, but I just need to find what's the p and x, right? So P is the probability of defectiveness, right? I'm looking for defectiveness. So in this case, defectiveness is the success. What is the probability of defectiveness? It's 100% minus 93%, 7%. As a decimal, because you need either a decimal or a fraction to put in this formula, I put in 0.07, right? N is the number of trials, right? How many trials do you have? You have 10 light bulbs. You have 10 trials. X is how many do you want to be successful? How many do you want to be the thing you want? So in this case, the thing that I want is defectiveness. I want 3 of them. Once that's there, why I'm saying the simple example, you're going to see question 2 and 3 and 4, you're going to do them much faster because, I already explained these things, and we'll be just hunting P and X and we're done, right? So you have P and N and X, and then you just put in the formula. So 10 C3, so 10 choose 3. If you have a Casio calculator, how do you put that NX in the calculator? So that's not a division, okay? There's no line in between the N and the X. So that's not a division. So it means N is a symbol for N choose X. So how would you put that C in the calculator? In a Casio calculator, you put the 10 first. So in brackets, you put the 10, and then to put the C, you hit the shift button and then the divide button. So let's put the C there. Again, to say that again, you put the bracket 10, and then you hit the shift and then the divide button. That gives you the C, and then you put the 3, you close the bracket. So that's the N, 10 choose 3, right? That's the N of NX thing here. So it's not a division thing. It's not 10 divided by 3. That would be wrong, right? It's 10 choose 3, right? So that's how we put in the Casio calculator. Other calculators may differ, right? You have to find that C button, right? And then just to continue with the formula, the next thing in the formula is P to the power of X. So P, whatever I called P, I just put it in 0.07 to the power of X. X is the number of successes. I put X is 3, put 3 times 1 minus P, 1 minus 0.07 to the power of N minus X, 10 minus 3. And then I just use equals in the calculator, I get 0.025, and I'm done, right? Looking at the other questions then, real quick, let's look at question 2. You have a multiple choice test. There's 4 answers. You have to pick one. So 1 in 4 chances. So that means P equals 1 in 4, or a quarter, or 0.25. So either the fraction version, 1 over 4, or the decimal, 0.25 work. Either one of them. That's what you put in the calculator, right? If the student guesses all of them, question, what is the probability that they get exactly 5 correct? So you want 5. That's your X. You want 5 successes out of 10. That's your N. So I just put that in. First, again, formula first. Put the formula. Write the P and X. In this case, P is 1 in 4, or 0.25. N is the number of trials, which is 10. X is the number you want to be successful, which is 5. Put that in the formula, and then you get 0.058. You do the same question 3. In question 3, the P, the probability, is 72%. Turn that into decimal, 0.72. And then the N is the number of trials. You're having 20 free throws, so 20 trials. And then you want 16 of them to be successful, so X is 16. Just put that in the formula, and then there you have it. So if you follow the formula P and X, if you find those three values, you're done pretty much. It's just a matter of not making a mistake putting in the calculator, right? And again, to put that C, you hit the shift and divide button. That's how you put the C, right? The choose. And then question four, it looks a little bit more complicated in terms of there's more words and there's more than three things, right? There's more than three numbers, okay? So there's the 91% and the 10%. And you might be wondering, okay, which one do I pick, right? So the 91% is just things to throw you off. So they tell you a company manufactures smartphones and 91% of them pass through quality control tests. We don't need to know that, right? So that's something to throw you off so that you can use that 91% as if that's your P, but that's not it. The probability that we actually want is the 10%. So however, 10% are found to be defective. So probability of defective is 10%. And we want to find 3 defects out of 13, right? So our P is 0.7. Probability of, our P is 0.1 probability of defect. Our N, the total number of samples that we're picking from is 13 or trials. And then X, the ones we want to be defective, is 3 smartphones, right? So it's the equivalent. So the 91% is just there to throw you off. Is the equivalent if I wanted to do that to throw you off in question 3, I would have had a sentence at the start that is saying, I recorded a basketball player throwing 1,000 baskets, trying to do 1,000 free throws, and they scored 720 of them, right? And then now I go on and then say that's the percentage, 72% and stuff. So I don't need to tell you how I got the 72%, right? All you care about is the statistic is 72%. I don't need to tell you that I measured 1,000 free throws to get 72%, or I measured 91% of the free throws, and then from that 91 I got 72%. I don't need to tell you that. So that's what they're doing in question 4. They're telling you how they got the 10%. They're telling you they took 91% of the smartphones. So let's say they're making 100 smartphones. They took 91 of them, and then they measured them, and they found that from the 91 of those, 10% of them, right, were defective. The key thing is the 10% were defective. That's what we care about. Right? We don't care how many you used. Did you use 91%? Did you use half of them to get the statistic? Did you measure all of them, 100 of them? We don't care. So that's just there to throw you off, but you recognize that if you understand the binomial trials, right? So you just put that in the formula then. 13, we're choosing 3, times the probability of defects, which is 0.1, to the power of the number of defects, which is 3, times the probability of not a defect, which is 1 minus 0.1, to the power of 13 minus 3, you get 0.142. Right? That's your answer. So let's just talk about another kind of question, another binomial trial question, similar to those. So here you have a multiple choice test, consists of 25 questions, and there's 5 possible answers, right? So you have A to E, something like that. And only one of them is correct, right? So Tom knows nothing about the subject, but he decides to take the test anyway. And he selects his answers of each question at random, right? And he picks, just pretty much guessing the test, and there's 5 choices, and they want you to find the probability that he gets exactly 5 of them right. Right, exactly 5. Okay, so so it's a binomial trial question. It's either success or fail. It's either they get it right or wrong, and you have a pool of choices. So you have, in each question, obviously you have 1 in 5. So you have 25 questions. That's the pool of trials. So you've been tried 25 times, and you have to get it right 5 times. That's the probability that we have to find. So to do that, then the formula always comes first. Once we recognize it's a binomial trial question, in this question it's easier to recognize it because they clearly told us use the binomial distribution. So it's kind of a giveaway that you're going to be using this formula, right? Kind of making it easier. If they didn't tell you that, then you still need to figure out that, okay, this is a binomial thing, right? And you just write P and X. P is the probability of you getting a question right. In this question, it is 1 in 5. So one answer is right out of the 5 they give you. So 1 in 5, or 1 over 5, or 0.2, whichever one, it's either decimal or a fraction that this formula takes. And then N is the number of questions. You are going to be tried 25 times. And then X is the number you want to find the probability of. You want to find the probability of you getting 5 correct, right? So you put in the 5. If they said at most 5. Then you have to find the probability of 5, 4, 3, 2, 1, 0, and add them up, right? If they said at most 5, but they said exactly 5, so just 5. So we just have to do one probability. But then if they said like 5 or 4, then we do 5 and then we do 4. We add those probabilities, right? But in this case, it's exactly 5, so we don't have to do that. So we put in the formula to get 0.196. Part 2 of the question, again, it's asking if there were 6 possible answers, right? So there are 6 possible answers now instead of 5. So now it's A to F choices in each multiple choice question. And if there were 6 possible answers to each question, what is the probability now? So what does the probability become? One thing is, first, expect a smaller number than you got before, because you're kind of making the odds lower, right? Before we got 0.196 or something like that. So if it was me just a check when I get my answer I expect a value lower than that, because it's been coming harder. You now have 6 choices, so you now have more possibilities of failing, of missing it, right? Of getting the wrong answer. So I do the same thing again, write down the formula, write down P and X. So in this case, my X, I still need 5 questions to get that right? I still need to get 5 questions right. So X is still 5, and there's still 25 questions in this, right? That are being tried. There's still 25 tries. P, but the probability now is lower, right? It's 1/6, 1 in 6, right? Because there's now 6 possible answers. So that's the only thing that changes from before. I put in the formula, everything remains the same, the 25 and the 5, but the chance, the P, is now 1/6. And then I just put 1/6, I get a value 0.178. It's lower than the 0.196 that I got before, which in my head kind of gives me confidence that this is probably right, because I expected the value to be lower, right? You have lesser probability, right? And then you have question 7 there. Question 7 sounds like you need to use binomial trials, but you don't, right? So it seems like that because it is the buzzwords, it is exactly and stuff. But how do you know it's different, right? So question 7, you have 3 milking machines fail independently during operation with probabilities of failure of 0.6, 0.2, and 0.1 respectively, right? So you can call these machines machine A, machine B, machine C respectively. So A has a probability of failure of 0.6 and so on. The question is, what is the probability that during a particular milking operation exactly one of the 3 machines fail? Okay, so in this case, you might be like, okay, it has the exactly thing, and they give me the probability of failure and stuff. So, this means that, it's a binomial, but, you don't have this idea of, there's a pool of trials. There's no trials here. Like, we try this machine 10 times. What is the probability that it will fail 5 times? That would be binomial trial, right? But in this case, it's not a trial. They're just telling you this is how often this thing fails, or this is the chance of this failing. What is the chances that 2 of them fail at the same time? It is not a trial. You're not saying how many times how many times out of 10 would it fail. Then it would be a trial, okay? So it's not, right? So it's not that. So that's how I recognize it. And another giveaway is that there's 3 different machines. There's 3 different things. So, that also that are independent. That also tells you that, maybe stay away from binomial trials, right? It could be more complicated to do it that way, or impossible, right? So in this case, it seems that you have to write the logical thing here. What does exactly one of the 3 machines failing? So what does that mean in English? So it means we want to find the probability that exactly one of these events occur. So there's 3 possibilities, right? Of course, you don't know if there's going to be 3 possibilities, but just find the possibilities, right? So exactly one machine failing means it's either A fails and B and C doesn't. Makes sense, right? One of them fails. Exactly one. So you can't have A and B failing at the same time, because that means 2 failed. They want exactly just one failing. You can't have A, B, C all working, because they want one of them to fail. So you see the A is the one that takes that takes one for the team and then fails, and then B and C don't, right? Or this time B fails and A and C, they have to not to fail, because you just want one of them to not fail. And then 3 is the other way, where C fails and the other ones are working. Those are the only three possibilities that exactly one machine would have failed. So just mapping it out in your head, writing it in your own words, whatever you want, you find out that there's three possibilities, right? And once you have this, you're pretty much done. You shouldn't give up on the question now, because all you have to do is find the probability of A failing, B not failing, C not failing, and line 2 and line 3, add them up, because those things, it could be that or that or that. When you hear or in probability, it means add. And when you hear and, it means multiply. Like for example, scenario 1 there that is saying machine A fails while B and C don't. You hear the and, right? So A has to fail, and B has to not fail, and C has to not fail. That has to happen at the same time, right? So that when you end, you multiply, right? So to get the probability of scenario A there, I multiply A failing times B not failing times C not failing. That will be probability of scenario A happening, right? So, and again, to just remind, so we have to calculate the probabilities of those three scenarios, add them up, and then it's just to remind you that if I know the probability of failure, I also know the probability of success, because the total has to be 1, right? It's either you succeed or you fail. In this case, the machine is either it's working or it's not, right? So if I know that A fails 60% of the time, or 0.6, that means it's operational, or it succeeds 40% of the time, right? So it's just 1 minus 0.6, I get 0.4. The same for B. B fails 0.2%, or 0.2 times, or 20%. So that means 80% of the time B is okay. C, if it fails 0.1%, 0.1 times, or 10%, that means 90% of the time C is okay. So I know both of them by just taking it away from 1 or 100%. Right, so if I want to do scenario A or scenario 1, which is saying machine A fails while B and C don't, I find probability of A failing, I was already given, is 0.6. Multiply, because this has to happen at the same time, multiply by the probability of B not failing. So B not failing would be 1 minus 0.2, right? And then times the probability of C not failing, it would be 1 minus 0.1, right? Just take away the probability of failing from 1, and then you get the probability of not failing. So scenario 1, which is this, number 1, the probability of that would be 0.6. A fails times 0.8. B doesn't fail times 0.9. C doesn't fail. I get 0.432. So 1/3 of that is done. And then the next thing is, I'll just do number 2. Number 2 is saying machine B fails. So B failing means just the 0.2, right? I already know that. So that's the 0.2 here. And A will not fail. So that means 1 minus A failing. So that's 1 minus 0.6. That will be 0.4. So 1 minus PA, it means 1 minus probability of A failing, 0.4. And then times C not failing. So C failing is 0.1. So C not failing would be 1 minus 0.1, which is 0.9. So I have 0.072. If I multiply those numbers, 0.4 times 0.2 times 0.9, I get that. And the last thing is, the last scenario, A doesn't fail, B doesn't fail, and then C fails. So C is the only one that fails, so 0.1, and then B doesn't fail, 0.8, A doesn't fail, 0.4. Multiply those, I get 0.032. So I have the probability for the three scenarios that I put up, and then I just add them up, because it's either that happens, or number 2 happens, or number 3 happens, right? So I add them up because they're mutually exclusive. I add that up, I get 0.536. So that's the chances of exactly one of those 3 failing. So here you have another question, right? At most one of them fails. Okay, so at most, again, you can't use binomial trials, but you can use logical concepts, right? Just write the thing in English, right, the way you understand it. So what does that mean if I break it down? At most one of them fails. So at most means maximum 1 fails. So that means it's either 1 fail, which is the maximum, or none of them fail, right? Those are the 2 scenarios, right? If I'm telling you the maximum is 5, so my answer could be the 5, it could be the 4, the 3, the 2, the 1. It cannot go over 5, right? That's most. That's what most means. It can be under that. It can be 0, it can be 1, it can be 2, whatever, but the maximum is 5. So here, they're telling me that 3 machines are there. at most one of them fail. That's the probability I'm looking for. That means the maximum that can fail is 1. So you can either have 1 or 0 failing. So those are my two probabilities pretty much. So probability of exactly 1 failing. I cannot have more than 1, remember. Exactly 1, remember I already did that in the last question. I found out what is the probability of exactly 1 machine failing. I found it was 0.536. And then none of them failing. So I have to find that now. Find the probability that none of them failing. So it's either just 1 fails, or, again, or means plus, none of them fail. So I just have to find the probability of those and add them up. And that will be the probability of at most one of them failing. So we already calculated, like I said, the probability of exactly one of them failing. In the previous question, we found 0.536. And then now we just have to find exactly none of them failing. So none machine failing. So that means A, we have to pass, B has to pass, and C has to pass at the same time. So that means I have to multiply those probabilities of A passing times B passing times C passing, and then that'll be the chances that none of them fail, right? So the probability that the first machine or machine A does not fail will be 1 minus it fails. So we already told the probability of failure is 0.6, so the probability of success is 0.4. I do the same for B, 0.8, the same for C, 0.9. Just multiply that, then that none of them fail, so 0.4 times 0.8 times 0.9, the answer is 0.288. That's the chances that none of the machine fails. Okay, and then now, so I have the probability of exactly 1 failing. We did that in part A, which is 0.536 in red there, and on the bottom now we just found the probability of none of them failing, which is 0.288. So now we just add them, because either that or this happens, right? So the chances quite high. You add 0.536 plus 0.288, you get 0.824 as the chances of at most one of them fails. So thank you for listening. See you in the next video.